I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss the definitions and terminology that is related to the module 2, Introduction to Solids and Semiconductors in the course Engineering Physics. So before going into details of the definitions, let us first look at what a definition is and why is it important to define the terms very correctly. So what is a definition? The act of defining or making something very definite, distinct and clear. That is the meaning of definition. Or in other words, you can put it as the formal statement of the meaning or the significance of a word or a phrase, just the same way as we find it in a dictionary. Or it is a statement expressing the essential nature of something. So this is what you need to know about a definition. Now coming to why is it important to define words. Why the definitions are very important? Because definitions enable us to have a common understanding of the subject. And they allow all of us to be on the same page when we are discussing or reading about an issue. Therefore, we need to make sure that we properly define our words and phrases so that all will understand. Coming to terminology. What is terminology? It is the body of terms used with a particular technical application in a subject of study or a profession. Now, what is the importance of terminology? Terminology plays a very important role in understanding the context and specialized texts. Understanding the intricate terminological details of the technical and scientific concepts help students to comprehend what the main message of the document is. Not only that, it also helps specialists to transmit the content in a very effective manner. So with this introduction, I just want to move on to the definitions and terminology of module 2. Module 2, that is Introduction to Solids and Semiconductors. So let us look at the brief outline of the topics. We have free electron theory, block theorem, then chronic penny model, origin of energy bands, intrinsic and extrinsic semiconductors, then carrier concentration in intrinsic semiconductor, carrier concentration in extrinsic semiconductors, and then the variation of Fermi level with temperature and with doping concentration. Means how the Fermi level varies if the temperature varies and if the doping concentration varies. And then finally the Hall effect. So we are going to discuss the definitions and terms or the terminology that is related to all these topics in this lecture. So let's go. So the first one is define the term conductivity. So how do we define conductivity? The ability of the material to allow heat and electricity to pass through it. So if the ability of the material to allow heat and electricity to pass through it is more, means its conductivity is high. And if its ability is less or it does not allow heat or electricity to pass through it, then its conductivity is very low or no conductivity in some cases. Now it works with both physical moments of electrons and also the transfer of energy between the electrons. How this conductivity happens is by physical movement of electrons and also by the transfer of energy between the electrons. Next, define the term electrical conductivity. We have seen a generalized term conductivity. Now we are going to discuss about electrical conductivity. So electrical conductivity, it is just the reciprocal of resistivity. So it is the ability of the material to pass an electric current through it. So here we are talking only about electric current. So it is the ability of the material to pass an electric current through it, and its SI unit is Siemens per meter. Now when I talk about resistivity, first you should know about resistance. Resistance is what? It is the resistance offered to the flow of electrons in a circuit. So whenever we write R, R is equal to rho L upon A. So here rho is the resistivity. Rho is what? It is the resistivity. And how do we write the formula for rho? Rho is equal to RA upon L. So here if you write the unit for resistivity, resistance is measured in ohms and area measured in meter square and length in meter. So we have meter. Now when we are talking about conductivity, if I represent it by sigma, it will be 1 upon rho. So conductivity is the reciprocal of resistivity. So it is 1 upon rho, or I can write it as simply L upon RA. And the unit will be 1 upon ohm meter. So 1 upon ohm, we are calling it as Siemens. So the other term we are using here is Siemens per meter. So that is why we are using the unit Siemens per meter. In electrical conduction, there is a real movement of electrons towards the positive electrode. So we know whenever we see in a circuit where there is flow of electrons, there is current. And how do the electrons flow? They flow towards the positive electrode and thus constitute the current. Now define thermal conductivity. So here we are going to talk about thermal conductivity. So the rate of flow of heat is the thermal conductivity of that material. So what does it show? If the rate of flow is more, then the thermal conductivity is more. And if it is less, the thermal conductivity is less. So heat always flows from the body having a higher temperature to a body having lower temperature. Always. Just like you pour water, water always flows from a higher level to a lower level. The same way, heat always flows from high temperature to low temperature. So till they attain an equilibrium condition. So the simplest example you see is when you are adding hot water to cold water. Say you are taking water at 70 degrees Celsius and adding it to water at 30 degrees Celsius. So what is going to happen when they mix? There is transfer of heat or temperature from the hot body to the cold body, from hot water to cold water. And the entire water attains an equilibrium temperature. So that is what we are talking about regarding the flow of heat. Now state Bloch's theorem. Bloch is the name of the scientist. What this theorem states is, solutions to the Schrodinger equation in a periodic potential take the form of a plane wave modulated by a periodic function. So we need to understand some of the things here. First thing is the Schrodinger equation and the solution to the Schrodinger wave equation. And what is a periodic potential? And then what is a plane wave and what is a periodic function? So these are the terms you have to understand here in this definition. So if we talk about a crystalline solid, so whenever we are talking about crystalline solid, so you see when the electron is removed from an atom, it becomes a positive ion. So here we are representing the positive ions in a crystal. You see they are equally spaced. No? Then what happens here is, if you see an electron which is free, it can move inside the crystal. So we say it is moving in a periodic potential. Why periodic potential we say here? If you see in the second diagram here, when we talk about the potential at the positive ion sites, the potential is always minimum. If you see here, these are the positive ion sites. When we are talking about the potential, so the potential is minimum here at the positive ion sites and maximum in between the ion sites. So as an electron moves like this, when it is near the positive ion site, its potential is 0 and in between it becomes maximum, and when it reaches the next positive ion again it becomes minimum, and because they are equally spaced, it's a periodic potential. The potential varies periodically. Now when we see the solution of the Schrodinger wave equation is given by psi of k. We can write it as a e power ikx or ikr in 3-dimensional. So that will be the solution of the Schrodinger wave equation. Now, because of this theorem, what we are trying to say is, it will take the form of a plane wave that is modulated by a periodic function. So what is that modulating periodic function? It is denoted by uk of r. Here, when we are talking in terms of r, it is in 3-dimensional. X, Y, Z and T we have. When I'm talking about X, it is only in 1 dimension. So psi k of R represents the solution to the Schrodinger wave equation in 3 dimensions. So what we are introducing here is psi k uk of R, which is the periodic function. So how we are expressing now this function as a product of a plane wave and a function uk of R. And it has the same periodicity as the lattice. Whatever periodicity is there in the lattice, this function also has the same periodicity. That is what we need to understand. So this is the expression that is given by Bloch. So we call them as Bloch functions also. So the Bloch theorem states that the solutions to the Schrodinger wave equation in a periodic potential takes the form of a plane wave which is modulated by a periodic function. Now the next one is, what does quantum free electron theory state about the conductivity of metals? So we are going to see what is quantum free electron theory, and according to the quantum free electron theory, how the conductivity of metals can be explained. So, what we see is a conduction electron in a metal experiences constant or zero potential. Conduction electrons are what? Whenever an electron becomes free, no, when it is detached from the atom, it is free to move inside the metal. So, these free electrons, we are calling them as conduction electrons. So, conduction electrons are free electrons. That is why we are also calling it as free electron theory. So, it experiences a constant potential and free to move inside the crystal, and an infinite potential exists at the surface. So, what is the explanation given is, they said why the electron cannot come out of the metal. The reason is there is infinite potential at the surface, and the electron cannot overcome the potential to come out of the crystal. So only when it comes out, it will participate in conduction. So here the explanation given in free electron theory is, as long as the electron is inside the metal, it is experiencing a constant potential which we are considering it to be 0, and it is free to move inside. But only thing is, it cannot come outside because it cannot overcome the infinite potential barrier that exists at the surface. Now, the results of these modifications, what does it indicate? So, it indicates that not all free electrons would contribute to the process of electrical and thermal conductivities. So, if I say the electron is free, means does it conduct in electrical conductivity and thermal conductivity? No. So not free electrons, all free electrons cannot contribute. only a small fraction of the free electron gas would participate in such properties. So this is the outcome of this quantum free electron theory. So first thing is there are free electrons, and these free electrons are free to move inside the crystal, but they cannot come out because of the infinite potential that exists at the surface. And because of this, what is the result? All free electrons would not contribute to the thermal and electrical conductivities, and only a small fraction of the free electron gas contributes to these properties. Now define an ion. What is an ion? An atom or group of atoms that carries a positive or negative electric charge. So how does an atom become positive or negative electric charge? This is the basic question which all of you must be knowing. So whenever we talk about an element, so if an element is ready to lose the electron, it becomes positively charged or a positive ion. And when it is gaining the electrons, one or more electrons, it becomes negatively charged. So when it is losing, it becomes positively charged. When it is gaining, it becomes negatively charged. So for example, you see sodium. Sodium whose atomic number is 11. So what will be the configuration of it? 2, 8 and 1. 2 electrons in the first orbit, 8 in the second and 1 in the third orbit. So what does this denote? We all know that for stable configuration, the number of electrons in the valence shell has to be 8. We call this as closed shell configuration. So now this element is always ready to lose this one electron somehow. And if it is able to lose the electron, it becomes positively charged. So we call this as positive ion. So when it is ready to lose this electron, so it becomes positively charged and we call it as positive ion. Now the other example we take chlorine. Whose atomic number is 17. So how do we write the configuration? 2, 8 and 7. So 7 again is not a closed shell configuration. It needs one electron to complete the octet rule. So it is always ready to accept one electron. So when it is ready to accept one electron, so it becomes negatively charged. So it will become Cl minus. So we call this as negative ion. So atom or group of atoms that carries a positive or negative electric charge. How they are attaining this charge? By losing the electrons or gaining the electrons. So here we have seen the two examples of gaining and losing, how the ions are formed. Now, what is an electronic state? Electronic states are also known as energy levels, or energies are sites in an atom or a crystal where an electron can reside in. So in simple words, what we say whenever you have to define the structure of an atom, we say that there will be a nucleus at the center and electrons revolving in fixed orbit. So we will have electrons in fixed orbit. So there may be 2 or more number of electrons. So the sites in an atom where the electrons reside, you call them as energy levels. So I will call them as energy levels. So the first orbit, second orbit and so on. So they exist in definite states. Now define the term energy band in semiconductors. So first of all, we will try to understand what a energy band is. Then we will talk with respect to semiconductors. So energy bands consist of large number of closely spaced energy levels. So we have discussed or we have seen what is an energy level now. If there are a number of closely spaced energy levels, then the bands can be thought of as the collection of individual energy levels of electrons surrounding an atom. So let us try to understand it with the help of this figure. Suppose we have two electrons. You see here in the first figure, there are two electrons. And we can represent the energy levels. This is one and this is one level. Two levels for two electrons. Now, if you are considering about three electrons, these three electrons, so the three electrons are denoted by the energy levels E1, E2, E3 and so on. Now, when we increase the number of electrons or the atoms here, so here we are seeing 8 atoms. So all the energy levels of the 8 atoms when we put together, they form closely spaced energy levels which will look like a band. And now when you see in an atom, in a crystal, if you see, there are n number of atoms. That can be Avogadro number of atoms if you see 10 power 23 atoms. Then all the electrons of all the atoms put together, there may be interactions between the electrons of the same atom or with the neighboring atoms. So what happens? These energy levels will be very closely spaced. And these closely spaced energy levels will form a band. And that is what we call an energy band. So energy bands are there in semiconductors also. If you see in a semiconductor, we have a valence band and a conduction band separated by a forbidden band, which we will discuss again in semiconductors. Now, what is a band gap? A band gap is the distance between valence band of the electrons and the conduction band. So, let us try to understand what is this valence band and what is this conduction band. Valence band is the range of energies, a band which corresponds to the range of energies possessed by valence electrons. So what are valence electrons? Those electrons which are in the outermost orbit, we are calling them as valence electrons, and the energies of all these electrons put together will form a band and we are calling it as valence band. And conduction band here means the range of energies possessed by conducting electrons form the conduction band. Now, if I see, if I have to show it as an energy level diagram, if this is the valence band, means I am showing the energies of all the electrons, valence electrons. So these are the levels which are closely spaced, which form the band. And now when these electrons become free, so the energies possessed by them will be shown by a band which we call it as conduction band. Now the gap that is there in between the two, the valence band and the conduction band, we call it as the band gap or the energy gap. So the band gap represents the minimum energy that is required to excite an electron up to a state in the conduction band where it can participate in conduction. So when we are talking about valence electrons are in the outermost orbit. When they are free, only then they conduct. Then we are calling them as conduction electrons. And what we have here in this is the conduction electrons, the range of energies possessed by conduction electrons. Suppose if I have an electron in the valence band, so what is the energy that has to be supplied to this electron so that it goes to the conduction band? So it will be the difference in energy that has to be supplied. So it represents the minimum energy that is required by an electron to excite into the conduction band. Suppose I say here it is at 5 electron volt. And this is 6 electron volt, means there is a gap of 1 electron volt. So how will this electron move into the conduction band? What is the minimum energy that we have to supply is the band gap energy, that is 1 electron volt. So that is what we are trying to understand with the help of band gap. Now define the term valence band. We have already seen. So let us see the exact definition. It is the outermost electron orbital of an atom of any specific material that electrons actually occupy. So outermost electron orbital, we are calling it as a valence band or the valence energy. Because now when we are talking about a crystal, there are n number of atoms which is giving rise to a band. So the range of energies possessed by valence electrons contribute to the valence band. So the valence band is the band of electron orbitals that electrons can jump out of and move into the conduction band when excited. So the electrons which are there in the valence band, they can jump out of the valence band and move to the conduction band when they are supplied with energy. That means when they are excited. Now define the term conduction band. What is a conduction band? Conduction band is the band of electron orbitals that electrons can bounce up into from the valence band. So the converse. So now from the valence band, the electrons can come into the conduction band. So it is a band of electron orbitals into which the electrons can come now from the valence band. So it is the range of energies possessed by the conduction electrons. So at the point when the electrons are in these orbitals, they have enough energy to move freely in the material. That is why we are calling them as free electrons or conduction electrons. So as long as they are in the valence band, they are bound. But when we supply energy and excite them, they become free. So when they are free, they are in the conduction band. So when these electrons are in the conduction band, we are calling them as conduction electrons. Now, what is a conductor? In terms of energy gaps, we are going to define now. If you talk about a conductor, in simple words, you can say which allows the heat to flow through it or the current to flow through it is a conductor. But how do we explain it with the help of the energy band diagram? So, according to band theory, a conductor is simply a material that its valence band and conduction band overlap. So, in a conductor, the valence band and the conduction band will overlap with each other. What does it mean? When we say overlap, what is the meaning? Means there is no band gap between the two. Means the electrons from the valence band can freely move into the conduction band. So they can be made free very easily. Means they conduct whenever there are more free electrons, means it is a good conductor. So it allows the electrons to flow through the material with minimum applied voltage. Or here if you see, this is the valence band and this is the conduction band. Now the electrons which are in the valence band can move very easily into the conduction because there is no gap between the two. So conductors have partially filled valence band through which the electrons can move freely. So this valence band is partially filled. So the electrons can move very freely into the conduction band. Now the next one, what is an insulator? A material which has a large forbidden gap. If the gap between the conduction band and the valence band is big, then it is an insulator. If you see here, this is the valence band and this is the conduction band. And the gap between the two is the band gap, which is almost of the order of 7 electron volt. So there is a large forbidden gap or the energy gap in between the valence band and the conduction band. So the forbidden gap is very wide of about 7 electron volt. So this gap is about 7 electron volt. So that is why we call it as insulator. Insulator means a material which do not allow the current to flow through it or heat to flow through it. We call it as insulator. Why it is not allowing? Because there is a huge band gap between valence band and conduction band. So we have already seen that for electrons to move from the valence band to the conduction band, we have to supply energy, a minimum energy equal to the band gap. So these valence electrons cannot easily move to the conduction band. They cannot be made free easily with minimum energy or minimum voltage. They cannot be made free. So when there are no free electrons, so there is no conduction, means it behaves as an insulator. So if you see here, the valence band is completely full, but the conduction band is empty. There are no free electrons. Because there are no free electrons, it does not conduct. It does not conduct means it behaves as an insulator. Now define a semiconductor. What is a semiconductor? A material in which the forbidden gap is very narrow. That is of the order of 1 electron volt. So here you see the valence band. This is the conduction band. And there is a small band gap. This band gap is of the order of 1 electron volt. So now what we understand here is, if you supply an energy, minimum energy equal to 1 electron volt, the valence electrons can be excited to the conduction band. So when they are excited, when the electrons are excited, what happens? Some of them go into the conduction band. So you see here, the valence band is completely full and the conduction band is empty or unfilled. But when there is excitation of electrons, they move from valence band to conduction band. So these are the electrons or the levels that are filled by the electrons from the valence band. So here it becomes partially filled. This is also partially filled. So when they are moving, they start conducting. So semiconductors can be made to conduct by supplying little energy. Now define the term doping and dopant. So what do you mean by doping? The process of adding an impurity to an intrinsic pure material is called doping. So when I say intrinsic semiconductor means it is a pure semiconductor. It is a pure semiconductor. So in a pure semiconductor, suppose if I take silicon, so we will find silicon atoms equally spaced. All atoms are silicon. So if you see the crystal arrangement, we will just denote with 9 atoms of silicon. They are equally spaced. Now this is a pure semiconductor. Now if you are adding an impurity, so if some other element is added to it, for example, I will add gallium to it. So what happens? One of this silicon atom will be replaced with gallium. Means I have added an impurity, and this process of adding an impurity we are calling as doping. So when I am doping means I am adding an impurity to it. So, and the impurity that we are adding is called the dopant. So what is the dopant here? Gallium. Gallium is the dopant. So doping means the process of adding an impurity, and the impurity that is added we are calling it as dopant. Now define the term Fermi level. What is a Fermi level? Fermi level is the energy level which is occupied by the electron orbital at temperature equals to 0 Kelvin. So what is the maximum level that the electrons occupy at this temperature? We call it as Fermi level. And the level of occupancy determines the conductivity of materials. So if the level of occupancy is more, the conductivity is more. So in other words, we also use or define it as a term which is used to describe the top of the collection of electron energy level. What is the topmost energy level that is filled? We are denoting it as Fermi level at absolute 0. Now define the term Fermi energy. We have seen Fermi level. Now what is Fermi energy? The value of Fermi level at absolute zero temperature, that is minus 273 degrees Celsius, is known as Fermi energy. Or it is the maximum kinetic energy an electron can attain at 0 Kelvin. So at 0 Kelvin, what is the maximum kinetic energy the electron can have? That we are calling it as Fermi energy. And this Fermi energy is constant for each solid. It depends upon the solid we are considering. For different solids, it is different. So it is a constant for each solid. Now, what does the conductivity of metals depend upon? So the conducting property of a solid is not a function of the total number of electrons in the metal, but it is due to the number of conduction electrons called free electrons. So when I talk about conductivity, I cannot say if there are more number of electrons in a metal, it is more conducting. No. It all depends upon the number of free electrons. Even though there are electrons and the electrons are not free, it does not conduct. So it does not depend on the total number of electrons, but it depends upon the number of conduction electrons or the free electrons. Next one, explain Hall effect. What is Hall effect? Hall is the name of the scientist. So who demonstrated this effect for the first time? So let us try to understand what is this Hall effect. It is the production of a voltage difference across an electrical conductor, transfers to an electric current in the conductor and an applied magnetic field, which is perpendicular to the current. So what we understand here is, when we are taking a material which is carrying current and it is subjected to a magnetic field in a direction perpendicular to the flow of current, an electric field is developed in a direction which is perpendicular to both electric field and magnetic field. So let us try to understand it with this. Otherwise it is very complex. It's a very complex sentence. To understand, we will understand it part by part. So we are taking a specimen or a material through which current can pass. So this block you see here is the conducting material we are taking. So when a material through which current flows, so this is the direction of flow of current along the y-axis. Now when current flows through this material like this, we are applying a magnetic field which is perpendicular to it. So this x is along the x-axis we have the electric current, and along the z-axis we have the magnetic field. So when we are applying these two perpendicular to each other, then what happens here is, it is subjected to a magnetic field in a direction perpendicular to the flow of current. An electric field is developed. How an electric field is developed? Because of the force that acts on the electrons or the charge carriers in the specimen. So what happens? These electrons will get separated. Suppose if we are having all the electrons being shifted or forced here, we have the holes on this end. So there will be a field that is developed between the two, electric field. And you can measure the voltage across the two by connecting a voltmeter. So this phenomenon, what we are observing here, we are calling it as Hall effect. And the voltage that is developed, we are calling it as Hall voltage. Why voltage? Means there is a difference in voltage, because this is at a negative potential, this is at positive potential. So positive is always at a higher than the negative. So there exists a difference in potential, or there is a potential difference which we can measure the voltage. So this is called as voltage. So to put simply, what we can say is, if you have a conductor through which current is flowing, and if a magnetic field is applied perpendicular to it, if these two are perpendicular to each other, the current and the magnetic field, so there will be an electric field that is developed in the perpendicular direction to both the electric field and the magnetic field. Means the three will now be mutually perpendicular. That is why we are denoting them by x, y and z axis. So along the x we have the current, along the z we have the magnetic field, and along y we are denoting the electric field. Now, how does a semiconductor behave at absolute zero? So, at absolute zero temperature, how does a semiconductor behave? It acts as an insulator. Means it does not conduct at all. Why? What is the reason? So, if you see the figure here, we are taking a pure semiconductor, a silicon. So, you can see the silicon atoms, 9 atoms we are representing. This is at 0 Kelvin. So now at 0 Kelvin, what happens? These silicon atoms are bound with their neighboring atoms. All the electrons of one silicon will form covalent bonds with the neighboring atoms because they have only 4 electrons. So by sharing of electrons, they try to attain the stable configuration. So they form covalent bonds with the neighboring atoms. And if you see at 0 Kelvin, all the electrons are tightly bound by covalent bonds and there are no free electrons. So when there are no free electrons, there is no conduction, means it behaves as an insulator. So a semiconductor is a solid which has the energy band similar to that of an insulator. Means you see here the valence band with the valence electrons occupy all levels, but the conduction band is vacant. That is what we see in an insulator. So this is the reason why at absolute zero it behaves as an insulator. Now, does semiconductor act as an insulator in the presence of impurity? Means if we are adding an impurity to a semiconductor, how does it behave? Will it behave like an insulator or what? No. So the answer is no. Means it does not behave as an insulator. So when the temperature is raised or when an impurity is added, their conductivity increases. So how? How does it happen? How does the conductivity increase when we are adding an impurity? Because the question here is in the presence of impurity. So we have already seen the process of doping. So doping means it is a process of adding an impurity. So here to the silicon crystal, when the temperature is increased or if you are adding an impurity, suppose I add a trivalent impurity gallium, which has only 3 electrons, then this is a hole. So this bond is broken. So this electron becomes free. Then what happens? It can move inside the crystal, which gives rise to conductivity. So the conductivity increases. So whenever we are adding an impurity, its conductivity changes, it increases. You see in the diagrammatic representation of the band diagram also, some of the electrons have gone to the conduction band, they have become free. So it will start conducting. So it does not behave as an insulator. Now, how is the resistance of a semiconductor classified? Semiconductors have negative temperature coefficient of resistance. Means if the resistance, as the temperature increases, the resistance decreases. Means the conductivity increases because conductivity is the reciprocal of resistivity. So what is the reason? When the temperature is increased, a large number of charge carriers are produced due to the breaking of covalent bonds. So when the temperature is increased, the bonds are broken. So when the bonds are broken, the electrons become free. So when they are free, they start conducting. So as the temperature increases, the resistivity decreases and the conductivity increases. Now, what are charge carriers in semiconductors? Now, if you see a conductor, Electrons are the charge carriers. Whenever we are talking about a conductor, it is due to the flow of electrons, and electrons are the charge carriers. But now if we see in semiconductor, both electrons and holes are the charge carriers. Only thing is, depending upon the type of semiconductor, sometimes electrons are the majority carriers and sometimes holes are the majority carriers. We are going to discuss about it in the next few slides. So, in semiconductors, both electrons and holes are the charge carriers. Now, which column elements are combined to make compound semiconductors or impure semiconductors? I can say impure. So, the compound semiconductors are made by combining third or the fifth column or the group elements. So, if you are taking a pure semiconductor like silicon and add to it either the third group element like gallium or a fifth group element like phosphorus or arsenic, you will get a compound semiconductor. So when I am adding gallium, we may get it as gallium arsenide, a compound. So gallium arsenide is made by combining the third and the fifth group elements. So we will be using either the third group or the fifth group elements for doping. Now, how are the charge carriers produced in extrinsic semiconductors? So, till now we have seen intrinsic semiconductors. So, what are extrinsic semiconductors? They are impure semiconductors. How do we make them impure? By adding an impurity. What is an impurity? An element which is not from the same substance. No? So, to a silicon, to a fourth group element, if we are adding an element from the third group, it becomes an impurity. So, impure semiconductors in which the charge carriers are produced due to impurity atoms, we call them as extrinsic semiconductors. And how do we get? They are obtained by doping. Means by adding an impurity to an intrinsic semiconductor, we get an extrinsic semiconductor. Now, which type of material is obtained when an intrinsic semiconductor is doped with pentavalent impurity? If we are talking about a pentavalent impurity, what is pentavalent? Means it has got 5 valence electrons. Pentavalent. Penta means 5. Valent means represents the valence electron. So, an element which has got 5 valence electrons means which belongs to the fifth group. A fifth group element will have 5 valence electrons. So, whenever we are adding a pentavalent impurity, it becomes an N-type semiconductor. So, N-type semiconductor is obtained by doping an intrinsic semiconductor with a pentavalent impurity. So, what are these fifth group elements? Example, phosphorus, arsenic, antimony. All these are examples of fifth group elements. Now the next one. What type of material is obtained when an intrinsic semiconductor is doped with a trivalent impurity? Trivalent means 3 valence electrons. 3 valence electrons. Tri represents 3. So when we are adding an impurity which has 3 valence electrons, that is any element from the third group. Example, gallium, boron, indium, aluminium, all these are examples which we take from the third group. So, whenever we add a third group element, it becomes a p-type semiconductor. So, p-type semiconductor is obtained by doping an intrinsic semiconductor with a trivalent impurity. Now, define the term hole in a semiconductor. What are holes? A hole is nothing but an absence of electron in a particular place in an atom. So, when we are talking about electrons and holes in a semiconductor, so hole is not a physical particle, it is only an absence of electron. Like we have seen here, when the temperature increases, the bonds are broken. So the bonds are broken means the electron becomes free. So when there is a free electron, means the electron has moved out from this position. So the absence of electron here, we call it as vacancy or hole. So what is a hole? It is nothing but the absence of an electron, the site where an electron is removed from. It is the vacancy or a hole. Define the term resistivity. So resistivity commonly symbolized by the Greek letter rho. And quantitatively it equals to the resistance R of a specimen, such as a wire, which is multiplied by its cross-sectional area and divided by its length. So we have already discussed this formula. We have seen R is equal to rho L upon A. So what is rho we have seen? R A upon L. So it is the product of resistance and area. So multiplied, R multiplied by A and divided by its length. So the same thing we are putting it in words. Rho is equal to R A upon L, R into A upon L. So the unit of resistivity is ohm meter. Because for the resistance we are writing ohm, and for area we write meter square, and for length we write meter. So the unit will be ohm meter. Now explain about potential barrier. What is a potential barrier? A region in which particles are decelerated or stopped by a repulsive force. That is what we call as potential barrier. Means if I am talking about a potential well in which we take an electron, there is an electron which is moving inside the potential well. So this electron can move here and it cannot penetrate and move out because there is an infinite potential here. So this is stopped at this. So we are calling it as a barrier or a potential barrier. So the same way when it comes here, again it is stopped here. So this is the barrier. So I can say these are the limitations for the electron to move. So we are calling them as potential barriers. Now define the term mobility. What is mobility? Mobility of electrons in a semiconductor is defined as the ratio of drift velocity to the applied electric field. So we can talk in terms of the ratio of drift velocity, which is denoted by Vd. V suffix D represents the field drift velocity to the applied electric field. That gives the mobility, which we denote by mu generally. Now define the term drift velocity. So how do we get the drift velocity? The average velocity attained by the charged particles like electrons in a material due to an electric field. So whatever the velocity that is obtained, the average velocity of all, means you take the average of all the velocities, drift velocities, you get the average. So that average velocity, we are calling it as the drift velocity. And the unit is the same as velocity, it is meter per second. It is also measured in meter square per volt second. So generally we denote it by meter per second. Now what is drift current? Drift current is the electric current or the movement of charge carriers which is due to the applied electric field. Often we call it as the electromotive force over a given distance. So whenever you are pushing the electrons or whenever the current is due to the applied electric field, then we call it as drift current. So when an electric field is applied across a semiconductor material, current is produced due to the flow of charge carriers. So when the charge carriers are moving, then you have the electric field. Now define Hall voltage. We have already seen the Hall effect. So we will see what is Hall voltage. So when a material carrying current is subjected to a magnetic field in a direction perpendicular to the direction of flow of current. So we will first see only this. So we have the conductor, or this is the material which is carrying current. So this is the current which is flowing in this direction I. And we have a magnetic field. This magnetic field is perpendicular to the direction of flow of current. Then what happens? An electric field is developed in a direction perpendicular to both. So if this is along the x-axis, this is along the z-axis, now we have a field that is developed along the y-axis. So these three are mutually perpendicular to each other. We are calling it as the Hall effect. And because of the electric field that is developed, there is a voltage difference between the two, the top layer and the bottom layer. Because the charges are separated, you have the electric field, and which gives rise to voltage, which we call it as the Hall voltage. Now define Lorentz force. What is Lorentz force? When a magnetic field is present, the charge carriers experience a force. So whenever we are talking about application of a magnetic field and an electric field, these two act perpendicular to each other. And because of these two, the charges will experience a force perpendicular to these two. So we are calling it as Lorentz force. It is the combination of electric and magnetic force on a point charge due to the electromagnetic field. So which we call it as the Lorentz force. Define the term charge carrier. What is a charge carrier? It is a particle or a quasi-particle that is free to move and carrying an electric charge. Because it is carrying charge, we are calling it as charge carrier. So what is the charge carrier? What is that particle? It can be an electron. If you are talking about a semiconductor, it can be both holes as well as electrons. So examples can be electrons or ions or holes. These will be the charge carriers in semiconductors. Now, what is an N-type semiconductor? It is defined as a type of extrinsic semiconductor which is doped with pentavalent impurity. What is a pentavalent impurity? It has 5 electrons in its valence shell. So, N-type semiconductor means it is doped with pentavalent impurity. Pentavalent impurity. Pentavalent impurity means it has 5 valence electrons. So these are the 2 points we have to remember. And electrons are the majority carriers. So in N-type, the majority carriers are electrons. We have 2 types of charge carriers we have seen, electrons and holes. So in N-type, electrons will be the majority carriers. Then what is a P-type semiconductor? It is defined as an extrinsic semiconductor. Extrinsic means impure semiconductor. It is doped with a trivalent impurity. What is a trivalent impurity? Which has 3 electrons in its valence shell. So a P-type semiconductor is formed by doping a pure semiconductor with a trivalent impurity. So when you are doping, it becomes an extrinsic semiconductor. In extrinsic semiconductor, there are 2 types. What we need to understand here. Extrinsic semiconductor means we have N-type and we also have P-type. So in N-type, we are doping it with pentavalent impurity. In P-type, we are doping it with trivalent impurity. Pentavalent means 5 valence electrons. Trivalent means 3 valence electrons. And here in this case, electrons are majority carriers. Electrons are majority carriers. And here, holes will be the majority carriers. Holes will be majority. So these are the things we have to understand. Holes are the majority. If you understand this points, you can define a P-type semiconductor, N-type semiconductor, what is extrinsic, what is intrinsic. 9. What is Hall coefficient? Define Hall coefficient. Hall coefficient is defined as the ratio of induced electric field to the product of current density and applied magnetic field. So we denote the induced electric field by EH. EH denotes the induced electric field. And the current density is denoted by J. J denotes the current density. And B represents the magnetic field. The magnetic field is denoted by B. So what the statement says, it is the ratio. Ratio of what? Electric field to the product of density, current density and magnetic field. So BJ. So it is EH upon BJ. It is the ratio of electric field to the product of the magnetic field and current density. So RH here represents the Hall coefficient. It is a characteristic of the material from which the conductor is made, and its value depends upon the type, number and the properties of charge carriers that constitute the current. It all depends upon the type of material we are taking. Now what is Hall effect? So simply we have already seen this. If a magnetic field B is applied to a specimen of thickness T carrying current I, a Hall voltage VH is developed. Then the Hall coefficient is given by RH is equal to VHT upon BI. So VH is the voltage that is developed, B is the magnetic field, I is the current, T is the thickness. So when you have a conductor to which a magnetic field and current are perpendicular to each other, there is a voltage that is developed along its thickness, and we can find the Hall coefficient using this formula. Then define what is charge carrier concentration. It is also known as charge carrier density. Charge carrier density or charge carrier concentration mean the same. It is the number of charge carriers per unit volume. What is the number of charge carriers which are there in unit volume? That is why we are calling it as charge carrier density. And its unit is measured per meter cubes, means the number of charge carriers per unit volume. So per meter cube. So its SI unit is the number per meter cube. Now define intrinsic carrier concentration. So what is this intrinsic carrier concentration? The number of electrons per unit volume in the conduction band or the number of holes per unit volume in the valence band. That is what we are calling it as intrinsic carrier concentration. So I think we will stop here and I'll see you in the next lecture. Thank you and see you.
Like, share and subscribe. Hit the bell icon for more updates.